Alright, so our electron configurations then are like assigning addresses for our electrons that are spinning around each atom. So they're described then by writing the shell number. So you can see here, the numbers that are listed here is the coefficients or the shell number. So this is the N number, the row number. The next letter is the subshell. So this represents the 1s subshell. And the superscript in this case is going to represent the electrons that are housed within that specific orbital. So there's 2 electrons that are housed inside the 1s orbital of beryllium. And then beryllium has a total of 4 electrons. And so the next 2 electrons are going to be housed in the 2s orbital. And the next 2 electrons are housed in the 2s orbital. So this is written, the electron configuration is then written 1s2, 2s2. And we can also designate and show our electrons drawn out as arrow diagrams. So we could say that there are 2 electrons in the 1s orbital, and you can see the electrons written out here, and 2 electrons in the 2s orbital. You could also do a shorthand by writing the closest noble gas that precedes or comes before the element that you're designating your electron configuration for. So if we look back at the periodic table, we'll see that helium is the noble gas that comes before beryllium, and the electron configuration for helium is 1s2. So we could say that the electron configuration for beryllium is essentially helium plus the 2 electrons that are housed within the 2s2 orbital. So writing shorthand for this one is not a big deal because this one is a very short electron configuration. But once you get into atoms that have a large number of electrons, writing the shorthand using the noble gas configurations becomes very useful. Saves you a lot of time to write them out that way. So the Aufbau principle that we talked about tells us that electrons have to go into the lowest energy orbitals first. And so these typically are the ones that are going to be closest to the nucleus of the atom. However, they don't always go in the order of the shells that are present. So if we look at the actual energy level of the different orbitals, what we see is the 1s orbital has the lowest energy, and it's in the first shell. And so this one would get filled first. The next lowest energy is going to be in the second shell, and this would be the 2s orbital, followed by the 2p orbitals. So remember, there's 3 orbitals that are present within the p subshell. So you can house a total of 6 electrons at this position. The next lowest energy is 3s and then 3p, and so this kind of is going in order. The third shell level has a d orbital as well. However, it actually is higher in its energy state due to the shape of the d orbitals than the 4s spherical orbital in the next shell level. And so instead of filling the 3d orbitals first, you're going to end up filling the 4s subshell first. Then you'd fill the 3d orbitals, and then the 4p, and then the same thing happens with the 4d orbitals. They are higher in energy than the 5s orbitals. So the 5s orbitals have to get filled first. So this overlap in energy level starts occurring at shell 3 and 4. And so we have to make sure that we take into account how to do this. And this is actually a very nice diagram. You can recreate this very easily. It's kind of like solitaire, and so I'll write this out for you in another demonstration. And what we can see is if we put all the s orbitals on the top, 1 through 7, so these are our shell numbers and then the s orbitals. And then the first shell does not have a p orbital because it's too small and too close to the nucleus. So we fill out all the p orbitals in the second row. And then the second subshell is too small to have a d orbital, so we skip this place here, and then we put in all the d orbitals, and then all the f orbitals. And if you go through and put in diagonal lines, these are the order of the shell filling and the order of the energies. So first you fill 1s, and then you come back down and you fill the 2s, and you come back down, and then you fill the 2p and the 3s orbitals. Then you come back down, fill the 3p and the 4s orbitals, come back down, filled. Now the 3D gets filled. So the 4s gets filled before the 3D. So the 3D gets filled after the 4s. And now the 4p gets filled. And now you can see the 5s is going to get filled before we come back down and fill the 4D. The 5p, the 6s get filled before you start filling the 4f subshell, and then so on. So that follows Aufbau's principle, saying that the lowest energy subshells get filled with electrons before the subshells that have higher energy. Another principle that we have to take into account is Hund's rule. So when there are orbitals of equal energy in a subshell to fill, the electrons are going to first go into different orbitals with parallel spins one at a time. And so essentially what this means is if you have open apartment buildings here, open orbitals, a single electron will fill each open apartment before they start to pair up. Okay, because you've got repulsion between the electrons, and so they don't like to live together if they don't have to. So if you've got equal energy orbitals, you're going to get electrons filling each of these separately first before they have to start pairing. So boron has a total of 5 electrons, and so we could see that from the periodic table. It's going to match the Z number. And so we start filling the s orbitals in the first level have to get filled first. So we've got 1s2, and now the 2s2 is going to get filled. And now there's only one electron that's going to end up in the p orbitals of the second shell. So this one is going to be represented here by this straight line. If we go down to carbon, which is the next element, it has 6 electrons. And so at this position, it's going to end in 2p with 2 electrons in there. And so instead of pairing with this electron that's already here, it's going to go into the next orbital over and be farther away from this electron. Same thing with nitrogen. It has 3 electrons that are going to end up being in the 2p orbitals. And you can see they each go into separate orbitals before they start to pair up. So if we continue on with oxygen, which has 8 electrons, 2 in the 1s2, 2 in the 2s2, and now 4 in the p orbitals of the second shell, you can see they have to start pairing at this point. And fluorine with the 5 electrons in the p subshell, and then neon, the noble gas, is completely full. And you can see that this p orbital is completely full. All of the electrons now have to pair. So this is Hund's rule, saying that electrons don't live together if they don't have to. So the periodic table is designed really, really efficiently so that you can easily figure out the electron configurations for any atom. And that's because the organization is going to correspond to where these different elements are going to end in their electron configurations. If they're in the main family in the first 2 positions, they're going to be s block elements, and they're going to end in the s block of their shell number. So all of the elements in this row here in these positions would end in 6s, 6s1 or 6s2 for this position. And we'll take a better look at this on the video in a couple of minutes. The only exception to this S block rule is the first subshell that only contains the S. You can see hydrogen would be up in this position here, and then helium is the only other element in this shell, and they are both s orbital electrons. But this one is now completely filled, and so we put it over here with the other noble gases, because all of the noble gases have completely filled outer shells of electrons. And that's a characteristic that's common to this group of elements. So helium, because it's full, is going to behave more like these other noble gases than it would the alkaline earth metals. And so we place it over here in the periodic table. The rest of the elements that are in the main group families, so the A group, 3 through 8, are going to finish in the p orbital of their shell. So this would be the 2p row, the 3p row, the 4p row, the 5p row, and the 6p row. The transition metals that are found in the middle are d block elements. So they're going to end in the n-1 for their shell level in that d orbital. So you can see that we are in the 4th row here, but this is the 3D subshell, so it's n minus 1 or 4 minus 1. And so all of these elements end in the d orbitals. So in their position along here, you can just count. You can go 1, 2, 3, 4, 5, 6, 7. This would end in 3d7 if you were at this position here. So it's very easy to be able to tell the electron configuration of any element within the periodic table. Our lanthanide and our actinide series are n minus 2 levels, and they are going to represent the F subshell, or the F orbitals. And so at the n minus 2 position, they start in the 6th and 7th row. So this would be 6 minus 2 would be the 4F subshells. And then in the 7th row, 7 minus 2 would be 5. And so these would be the 5F elements that would end here. So remember, we can separate our periodic table and make it much longer, and it would include those F orbitals up in here, the lanthanide and the actinide series. So we'll see some more examples in our video portion of how to actually place and calculate what the electron configuration is for the different elements.